starting by saying how beautiful you're all looking tonight, but I literally cannot see anyone, so I have no idea if that's true or not. My name is Holly. I'm a postdoctoral researcher at UNSW in Sydney, and I'm here to talk to you tonight about quantum computing. I know, wow. So, some of you may have noticed, if you're being very perceptive, that I'm not actually from Australia originally. Maybe my accent or my deathly pale complexion and red hair. But I love living in Australia. It's amazing. I get to live in a perpetual layer of factor 50 sunscreen. The spiders here are the size of my fist. And on special occasions, I even get to drink out of a shoe. It's fantastic. Okay, so enough about me. Let's talk about quantum computing. So some of you might have seen in the news recently, there's a big race in humanity to build the first quantum computer. Now, the embarrassing thing is, despite putting lots of money into this problem, we're actually not sure exactly what we should build a quantum computer out of yet. So my research is focused on building one specific way that we could build a quantum computer using the spin of group 5 donor atoms implanted via ion implantation into a silicon lattice. Thank you. Did not expect applause at that point. So a subsection of you who weren't applauding probably just completely zoned out at that point, but zone right back in for a second, because I'm here to tell you that in this specific type of quantum computing, Australia is actually leading the race at the moment. Okay? And not even by a lucky accident. So before I explain what my research is about, let's take a step back for a second and explain what is quantum in general. Now, the thing that I love about working in a field that has quantum in the name is whenever you talk to a non-scientist, there's a surprisingly high chance, this has happened to me many times, that someone will respond with something like, "Oh, no way, I love quantum." If this ever happens to you, ladies and gentlemen, buckle up, because you are about to hear the most batshit crazy explanation of what this person thinks quantum is. So for all of you who have experienced this, or haven't, I've come up with a handy guide of how to separate some good sources of quantum physics information and some bad sources of quantum physics explanation. For example, peer-reviewed articles. Good source of information on quantum physics. Scientific talks. Good source of information about quantum physics. University degree. Even better source of information. Marvel films. Bad source of information. Dishwasher. Bad source of information. Bill from Byron Bay, who runs a meditation workshop on quantum healing and will align your chakras. Bad source of information. So what is quantum physics? Well, generally speaking, the universe can be roughly divided into physics of the big stuff, like planets, footballs, and inflatable bin chickens. And then there's the physics of the small stuff, like molecules, atoms, and Donald Trump's tiny hands. Now, the physics that governs the big stuff is something called classical physics, mostly. And classical physics is the physics that we all know and love. It's the physics that describe why we stack it. For example, if we're parkouring across a very sketchy river crossing with a 10-kilo backpack, that falling in the river is explained by classical physics. That beautiful projectile motion of our vomit when we've had one too many shoeies, that is also classical physics. But when we go down to the small world, that's where quantum physics takes over. And quantum physics is completely outside of our everyday classical intuition, which is a fancy way of saying everything goes to shit at the small level. And I want to be more specific about the exact types of way that things go to shit. So the first way is something called superposition. Now, to explain superposition, I'm going to use the example of the quantum particle of Donald Trump's hands. So in the quantum world, Donald Trump's hands can be in many states at the same time. We call this a superposition of states. And it's only when we actually look at which state his hands are in, or make a measurement, that they decide which state they're going to be in. The other wacky quantum phenomenon is something called entanglement. And I will also be using Donald Trump's hands to explain this. And I know it's getting a little bit weird at this point, but I'm way too deep into this analogy to stop now. So let's say Donald Trump's hands, they can be in a state of either pointing up or down. Now we take two of his hands and we put them inside this entangling machine. Now they're very sad inside this machine because there are absolutely no women to grope in here. So the hands come out of this machine and they're entangled with each other. What the hell does that mean? Well, it means actually the hands have lost all identity of themselves, so they're no longer up or down. The only description the universe has now for these hands is that they're pointing in opposite states to one another. So now we can send one of the pair of entangled states of Donald Trump's hands to Perth, and we can keep the other one here in Sydney. Now, if we make a measurement of the hand in Perth, it'll decide whether it's up or down. And the cool thing is, the hand that's in Sydney will instantaneously know that we made a measurement of the hand in Perth, and it knows that it has to be in the opposite state. So if we measured the one in Perth to be up, the one in Sydney instantaneously knows it has to be down. Spooky, right? So Donald Trump, no. So Einstein called this spooky action at a distance. Now, what does this have to do with quantum computing? Well, in quantum computers are an entirely different type of machine to the classical computers that we use. So rather than using the laws of classical physics, they actually use the laws of quantum physics to operate. So they use these spooky concepts of superposition and entanglement. Now, there are some problems that we think are going to have a major advantage using quantum computers over classical computers. For example, we think that drug design could have a major advantage by using a quantum computer rather than a classical computer, or tackling certain issues to do with climate change, or optimization problems in finance and transport. These are all things we think will have an advantage. What we don't think will have an advantage is sending emails, for example, or trolling people on the internet. So sorry to any keyboard warriors out there. So what do I do in my research? Like I said, I use the spin of group 5 donor atoms as building blocks of this quantum computer. So to explain that, we're going to have to take a look at the periodic table. Like this 18th century Italian period table. If we take a look at this periodic table, we have two atoms of interest. One of them is silicon, and the other one is a group 5 atom, such as phosphorus. Now, silicon has 4 electrons in the outer shell, but phosphorus has 5. So that means 4 of the electrons in phosphorus form covalent bonds with the silicon, and we're left with one Billy No-Mate's loner electron left out. And rather than being a strong, independent electron, this one actually hangs around the phosphorus atom where it's not wanted. But this is great for us because it means we get 2 quantum bits, or qubits, for the price of 1. We get the phosphorus and we get the electron. So if we put these phosphorus and electrons inside a magnetic field that's roughly 1,000 times stronger than your average fridge magnet, we can actually use a fundamental property known as the spin of these atoms to encode our quantum information of zeros and ones. And we can create these cool superpositions of both 0 and 1 at the same time and entangle them together. So during my PhD, I put these devices inside this wacky-looking apparatus here, which is called a dilution fridge, or fridge for short. And these things can go down to a fraction of a degree above absolute zero, which, for reference, is actually colder than the average apartment in Canberra. And once we've cooled them down to these insanely cold temperatures, we then use radio frequency and microwaves to control the spin and create these weird entangled states between them. As a proud woman in physics, I'm not thrilled that I've ended up in an over-engineered kitchen consisting of fridges and microwaves. However, the fact that I've managed to control these spins has basically shown to the world that this is an excellent potential platform to build a quantum computer from. So now there's the very simple task for other people to do of moving from these 2 spins to maybe billions of spins that we're going to need in order to do a useful quantum computing task like trolling people online. But we're still a long way from that, but Australia is actually leading the world in this, so you guys should all be very proud of that. And if you take nothing else from this talk, let it be that Donald Trump's hands are an excellent measure for quantum information.